One of the most important operation in signal analysis is probably the convolution operation. So now let's try to understand what this convolution operation actually means, right? And so to understand a convolution, we need to understand two things. One is what we call the unit sample synthesis, and the other thing that we need to understand is what exactly is the linear time invariant system, or LTI, linear time invariant system. So so to understand the convolution, we need to understand these two things. And unit sample synthesis is kind of sort of expressed using this particular equation. It's not too complicated if I sort of try to explain it. It just means that any signal xn can be represented as a linear superposition of weighted and shifted impulse signals. So here it's actually an impulse signal. It's delta n subtract k, but it's a shifted impulse signal because the peak of this impulse sequence is actually located at k instead of 0. So it's basically a shifted impulse. And then it's also a scaled impulse because xk is actually the amplitude of the signal x at location k. And then there is a summation over k. So all you have to do is in order to actually construct any kind of signal, all you have to do is to do a weighted summation of those shifted delta pulses. And to show that, let's look at some examples, right? Let's look at some examples. So I'm gonna just clear up this particular figure, right? So let's try to generate a random sequence. For example, x equals to, it's just a random sequence with one row, three columns, three numbers, x three numbers, and n, that's the horizontal of x-axis. Let's just assume it goes from like a 5 to a 7. And then if we want to make a plot, we can sort of see it's just three sticks, right? And then you can actually represent this xn as a superposition of basically three shifted impulse sequences. So let me make a subplot, and then do a plot of the signal itself, right? And then maybe let me change the range. Let's move it from like a 1 to like 10. Let's give it a range so you guys can see that the signal is sort of in the middle. Right? And now let's try to generate a impulse. And we're gonna use x1 n1 equals to imp seq. And this impulse is gonna be shifted to the location 5. So basically we're gonna do each of the pulse at a time. Do one pulse at a time. So the first pulse is going to be centered at 5. And then the range, let's just suppose it goes from like 1 to 10. And then let's make a subplot of it. And then just a stem n1 x1. So that's our first pulse. That's our first shifted pulse actually. But it's not scaled yet because the amplitude is still 1. It's not scaled by xk yet, right? In fact, I should have made 4 subplots actually. And then (1 to 10), right? And then 2 stem n1 x1, right? That's our first pulse. And then let's try to generate the second pulse, x2 n2 equals to imp seq. But for the second pulse, it's gonna have shift that's amount of 6, and then let's still make the range from 1 to like 10. So stem n to x2 is gonna give you a powers. Oh, sorry, I should switch to a different subplot. That's n to x2, right? Again, it has an amplitude of unity. And then let's construct the third pulse. So x3 n3 equals to imp seq, and the third pulse should have a shift of 7. Goes from 1 to 10. The range goes from 1 to 10. And then subplot 4, 1, 4. And then let's just stem n3 x3. Right. So that's the third pulse. So that's just the 3 shifted pulses. 3 shifted pulses. The amount of the shift is actually the location where the input signal, the xn, has non-zero amplitudes. So to see, because input signal xn has non-zero amplitudes at just 3 different locations, 5, 6, and 7, right? So you basically construct a shifted delta pulse, a shifted impulse at those locations where x is non-zero. Because if for a location where x is 0, for example, at location 2, x has 0 amplitudes, it doesn't really have anything. Then the weights for that particular shifted pulse at x equals to 2, n equals 2, is going to be 0, so it's not going to contribute to the final summation, right? So now let's try to carry out the summation, right? So we have this is n1 x1, n2 x2, and this n3 x3, right? And then let's just add them together, but with a weight. And I'm gonna construct x4. So x4 is just gonna be x1 multiply with. So here x1 is actually the first non-zero element inside of the x, right? And then I'm gonna multiply with x1. x1 is sort of the shifted pulse, the first shifted pulse, right? And then plus x2. That's the second non-zero amplitude of x, right? And then multiply with x2, and then plus x3, the third non-zero element of x3, and multiply with x3. And then I've got my x4. What I claim is that x4 should be identical to x, right? So suppose I hold on. So suppose I subplot 4, 1, 1, and then hold on to the old plot, and then do another stem, but use a different color. I'm gonna do n x4. I'm gonna plot x4, but I'm gonna use red, right? So if those two signals are identical to each other, so the red sticks are gonna be on top of the blue sticks, and you won't be able to see blue sticks anymore. So it looks like I have an error message here because n has just 3 elements in it, but x4 actually has 10 elements in it, because x4 is like a superposition of x1, x2, and x3, and the size of x1, x2, and x3 is like 10, I think. So that's the reason it's actually reporting errors. So x4 actually has the same length as x1, x2, and x3, right? So what I have to do is to sort of stem. I'm gonna use n1. N1 has the same length, has the same range as x4. So, and you can sort of see the red stick and the blue sticks are sort of on top of each other. So this way that you know for sure that this particular expression is actually true, right? So any signal can be represented as a weighted superposition of shifted impulse sequences, right? Basically, that's this equation is telling you, right? So the weights happens to be the amplitude of the signal at each of the locations, and the amount of shift for the delta pulses happens to be the locations where x is non-zero. X has non-zero amplitudes because at locations where X actually has zero amplitudes, so if X at the location K actually equals to 0, then it doesn't contribute to the summation. So you have to sort of use the locations where X has non-zero amplitudes. So that's what we call the unit sample synthesis. The input or any kind of signal can be represented as a weighted superposition of shifted delta pulses or impulse sequences. Now let's look at the second thing that we have to sort of pay attention to. That's the concept of a linear time invariant system. So what exactly is a discrete system, right? Or what exactly is the system? You can think of a system as a black box where you take a input sequence xn, and then it's going to return a output sequence yn. And it's a quite abstract representation. So you don't really have to care about what this system actually is. All you care about is what's going to go into the system. In this particular example, it's xn, and what's going to come out of this system if you put this input into that system. That's, in our case, it's yn. And such an abstract representation is not particularly useful in practice. So to make it more useful, we need to impose some conditions about this system, which we call T here. In the rest of the slides, I'm going to use L, big L, capital A case L, because T, I use T here to represent a transformation. You are basically transforming a input signal to an output signal, right? And but in the literature, people often use L, the capital case L. So a discrete system L is linear if and only if it satisfies the principles of superposition. So what exactly is a linear system, right? Because so here you know why it's L. L represents linear. A linear system just means that if the input is a superposition of two signals, for example, x1 and x2, with some weights a1 and a2, and a1 and a2 could be complex numbers, but it's still a scalar. It's still a scalar, right? It could be real numbers, complex numbers, negative numbers, positive numbers, but it's a scalar. So it's basically a superposition of two signals, x1 and x2. A linear system has this kind of special property. So if the input is a linear superposition of two signals, then the output is going to be the same linear superposition of the output of each of the individual signals. So this is Lx1n is the output of this linear system if the input is x1n, and Lx2n is the output of the linear system if the input is x2n. And you can sort of see a1 and a2 is the exactly same coefficient that you used to add together x1 and x2. And then you are using exactly the same weight to add together the output of the linear system for x1 and x2. So basically, for a linear system, what you can do is that you can move this L operator onto each of the individual signals inside this linear superposition, right? If you look at the right-hand side, left-hand side, it's basically L applied on the whole thing here. If you look at the right-hand side, it's basically L applied on each of the individual component signals, right? Right. So essentially, you are basically just moving the L operator onto each of the individual input signals inside of this superposition, right? That's what we call the linearity of a system, right? And it turns out most of the systems that we studied today are either linear or can be approximated as linear. And so this this kind of linear assumption is actually a very useful assumption. And in practice, it's actually a quite useful assumption, right? It's almost universal. Most of the systems we study today are either linear or can be approximated as linear, right? So that's what we call a linear system. So if we have this linearity property for system L, and we express the input signal xn as a superposition of shifted pulses, then what's going to be the output, right? What's going to be the output? You can imagine you put L in front of the on the left hand side and apply L onto xn, right? And then you can put L in front of this summation. But because L is actually a linear operator, you can actually move that L onto the signal itself. And in this case, the signal itself is actually a shifted delta pulse. Xk is what? Xk is merely the coefficient. Xk is just like A1, A2 here. It's just a coefficient in front of the signal, in front of the multiplied with this impulse signal. So what you can do is to carry L to delta. So what you end up with is yn the output. The output signal, if your input signal is actually xn equals to this thing, the output is going to be xk, a summation of xk times applying the same system L, the same operator L, onto those shifted delta pulses, basically. So by assuming that your system is linear, you can already get some useful results about the output, right? So the input is basically a superposition of shifted delta pulses, and then the output is going to be a superposition of the output of the system if the input is a shifted delta pulse, right? So do you guys see the kind of usefulness? And the coefficients is exactly the same. You don't really have to change anything. Right? So by assuming the system is linear, you can put the operator L onto those shifted delta pulses instead of on the input signal xn, right? You can carry the L onto those shifted delta pulses, right? So that's the first property that we are gonna sort of assume for our system. We assume that our system is linear, right? That's the first assumption. And then we're gonna sort of deal with the second assumption, which is called a time invariant system. We're gonna assume that in addition to linearity, we're gonna assume that the system itself doesn't change with time. It means that the internal mechanism, if you treat the system as a black box, and then the internal mechanism, the internal implementation of the system doesn't really change with time. So if you put an input signal into the system today, you get an output signal. And if you put the same input signal to the same system tomorrow, you're gonna get exactly the same output signal, except that the output has been delayed by like 1 day, right? Because you put the input signal, you put the same input signal like 1 day later, right? So it's gonna be delayed by 1 day. So that's what we call a time invariant. So the output of a shifted input is gonna be a shifted output. So here, if you actually use xn as input, you get an output that's yn, right? If you shift the input signal, delay it or advance it by a certain amount of k, then the output signal is gonna be just the yn here shifted by exactly the same amount of k, the same amount that you shifted x by, right? You shifted x by k, and then the output is going to be shifted by exactly the same amount k. That's what we call a time invariant system, right? So in practice, this kind of time invariant assumption is also very useful. If it's not exactly true, you can also treat it approximately true if you actually consider smaller time segments. So the Earth is actually constantly changing, right? But if you consider geological scales, it's millions of years. So Earth is actually changing on a scale of millions of years, right? But if you consider the propagation of seismic waves propagates in a very short amount of time compared with the geological time scale. So in that very short amount of time, you can consider the Earth as approximately time invariant. So it's also a very useful approximation that you can actually invoke when when the system is actually changing, but on a very long time scale. But if you're and the phenomena that you're considering is actually on a much shorter time scale, you can also approximate that system as time invariant, right? But now let's look at if we have this particular time invariant assumption, what's going to happen to our system, to our sort of system, right? So we have L. Now it's both linear and also time invariant, and then we have a delta impulse as input. Assume that the output for this delta input, delta pulse, which is centered at zero, because you are not shifting it. We assume that the output is going to be Hn, right? This might be something that you can measure in practice if you are actually doing a system, if you are actually dealing with some kind of a man-made system, or in some cases in the natural system, you can measure it. It is something that you can either compute or measure, right? And this output is what we call the impulse response. And some people prefer to call it the Green's function. The Green's function. It looks like it types like the text for Green's function is like this kind of thing, because it's the person Green who actually invented this kind of notation. And some people prefer to call it transfer function, right? Transfer function, right? It has several different names, but essentially they mean the same thing. It's just if you put a delta pulse that's centered at zero into the system, and the output of that system is going to be called either a impulse response or a Green's function or a transfer function, that kind of thing, right? So if the system is actually time invariant, it's time invariant. It means what? If you shift the delta pulse by a certain amount of k, then the output is going to still be H. It's going to have the same shape, but it's going to be shifted by exactly the same amount of k, right? So that's the consequence of assuming that the system is time invariant. It doesn't change with time. So if you shift your pulse by amount of k, the output is still going to have the same shape, but it's going to be shifted by exactly the same amount of k. So that's what we call the time invariant system, right? And now let's put things together, right? And now let's try to sort of understand what convolution actually is. So in this previous slide, I actually have shown you if the input xn can be expressed as a linear superposition of delta sequences or impulse sequences with some weights. And then if the system is linear, and if you apply this linear system L onto this input signal xn, you can actually carry L to the delta, to the impulse sequences here, right? And then here I'm actually showing you if the system is actually time invariant, then L delta n subtract k is actually H n subtract k. It's actually the impulse response shifted by k. If you stick that expression here, then what you're actually getting is xk times H, the impulse response shifted by k. So that's exactly this the convolution representation. So yn, the output signal, is gonna be a linear superposition of L applied on shifted impulse. And then this shift, the output of L on a shifted impulse is going to be the shifted impulse response. And then this summation, this superposition is over k, which is basically all the locations where x has non-zero amplitudes. And the weights on it is just the amplitude of the input signal. And this particular summation, this particular expression, is conventionally denoted as convolution. So if we look back, what convolution actually is telling us is that what a convolution actually means. So what convolution actually means that if you can actually represent the input signal as a linear superposition of impulse sequences or shifted impulse sequences, right? Which is always possible. You can always do that. Then the output signal yn for a linear time invariant system is going to be a linear superposition of shifted impulse responses. That's what this convolution expression is actually telling us. And the weights is actually identical. The weights of the linear superposition is actually identical to the weights that you use for representing the input signal as a linear superposition of shifted delta pulses, right? So basically that's what convolution actually means. It just means that the input signal can be represented as linear superpositions of shifted delta sequences. Then the output signal for a linear time invariant system is going to be the same linear superposition of shifted impulse responses, which is denoted as H here, right? And that's what we call the convolution operation, right? So now let's try to implement this particular formula in Matlab, right? And let's see how we can actually sort of implement this thing as a function, as a function actually. So the first thing we're gonna do is to sort of try to validate this equation to show that it's indeed correct. I have a function that's already written. I have a function. Let me show you the function. COMV m.m. That's sort of the function. That's the function. It takes two inputs. Basically, the input signal x and its horizontal axis nx, and then h is basically the impulse response of the system, and then the horizontal axis of the impulse response, because the impulse response is also a signal, so it's gonna need a horizontal axis, which is denoted as nh here, right? So I'm gonna use this particular function. I will explain how this function was written, but let's try to sort of implement this particular formula in the command line first, and then see what's gonna happen, right? And then we're gonna compare it with the result that's generated by COMV_m. We'll compare the results, but first let me clean out the signal. And I'm gonna do three subplots, and then the first one is still nx, the signal that I just used to validate the impulse superposition of a sort of the unit sample representation of a arbitrary impulse, right? Let me change the xlim goes from like 1 to 10, right? So that's gonna be our input signal, and then let's try to generate a arbitrary impulse response. Let's just pretend we have obtained a impulse response for a certain system. Let's just assume that system is Earth or something, right? Let's assume. So H is gonna be, I'm gonna generate a random sequence with just one row and two columns, right? And then the horizontal axis for NH is gonna be from like a 1 to 2. And then in the second subplot, let me stem. I'm gonna plot this H, and then I'm gonna adjust the horizontal axis to exactly the same. So from 1 to like 10. So how are we gonna sort of implement this particular formula, right? Because x actually has three non-zero values, non-zero amplitudes, right? Each one of them at 5, the other one at 6, and the other one at 7. So this summation essentially involves k goes from like 5 to 7, 5, 6, 7. K goes from 5 to 6 to 7, because only at those locations x has non-zero amplitudes, right? And then that's h, right? In fact, we have to shift h. We have to shift h by 5, 6, and 7. So let's try to generate. So n1, no, h1 n1 is going to be a shifted h. So let's just call 6 shift h nh. Let's call it nh1, and then it's going to be shifted by what? The first amount of shift is 5 actually. I don't exactly remember how 6 shift was written. Let me just go back to. So the amount of shift is the last input. It's here. So the amount of shift is actually the last input. So what I have to do is to Right, so this is actually the correct call. Right, that's shifting the first impulse, shifting the impulse response by 5. Right, and then let's do H2, NH2, 6 shift, H, NH, shifted by 6, and then H3, NH3, 6 shift, shifted by 7. Right. Now we have to add those 3 signals together actually, and we have to multiply them with each of the elements that's in each of the amplitudes of the input signal, right? Because those shifted signals are gonna have different locations. So suppose I do a subplot 3, and then do stem NH1 H1. You can sort of see it has a range that goes from like 6 to 7. So if I do a xlim, so it has actually shifted the entire sequence to here. You see, because H is actually here. That's the H. But H1 that's being shifted by 5, it has been moved to here. You see, right? And then if you do an H2 xlim, that's being shifted even more. You've shifted this thing by amount of 6. So the impulse response starts at 1, right? But now it starts at 7 because it has been shifted by 6. You see, and then if you do stem 3 H3, 1 to 10, then it's gonna shift it by 1 more unit. It goes from like 8 to 9, right? Because 1 has been shifted by 7, so it comes to 8. You see, so that's the 3 shifted signal. Because the range is gonna be different, so let's use sig add. So we're gonna use sig add. So it's gonna be NH1 times, so it's gonna be X1 times NH1, and then N times H1, times H1, and then the horizontal axis is gonna be NH1, right? And then we will have to add it to X2 times H2, and then horizontal axis is NH2. But this is just a part of the summation. We're just summing together the first two signals, the first two shifted impulse responses, right? Let's store it into a temporary variable. Let's call it C1, CH1. Right? And then we'll have to add C1, CH1 to the third shifted signal, which is basically H3, NH3, right? Now let's call it C2, CH2 equals to sig add, which is basically C1, CH1, and then X3 times H3, and then horizontal axis is NH3. Right. So that's going to be C2, CH2. It's going to be our convolution result. Implemented using exactly the same formula here. So if I do stem CH2, C2, and then let me just change the range. Still let it go to from like a 1 to 10, right? So that's going to be our convolution result. And I was telling you that you can actually implement it using a function, and that function is called conv_m. I'm going to explain why I write this particular function instead of just calling the Matlab intrinsic function. It's called conv, right? But let's call this function first and try to validate our result, right? Let's call this particular function. Let's call it what's the way for calling it? Ny equals to conv_m, then the inputs, right? So I'm gonna call it ny equals to conv_m, and then that's gonna be our two signals x n, and then h nh, right? And then let's just sort of make a plot of it. I'm gonna still plot inside this sub window. I'm gonna hold on to this particular sub window, and then I'm gonna stem NY but with red. And then if I adjust the, and you can sort of see the horizontal axis. No, the red sticks are right on top of the blue sticks, so you don't see the blue sticks anymore. But they are actually identical. They are actually identical. So it means that this formula is actually correct. But now let's try to understand. How this function was written. So basically, I have a comment line here: modified convolution routine for signal processing. And then let me just write y and y equals to conv m x and x h and h. Right. Let me explain some of the, so x input signal nx horizontal axis of input of x, and then h impulse response of system, nh horizontal axis of h. Basically, that's going to be our documentation of this particular function, right? And then let's try to look at the lines, right? The most important line is, of course, this particular line. It's actually doing the convolution by calling the Matlab intrinsic function that's called conv, right? And then if you, in the command window, if you type help conv, it's going to display convolution and polynomial multiplication. So it's going to convolve vectors a and b. It's just going to do a convolution of two vectors or two signals, basically, right? And you can also give it some kind of options, right? Some kind of options. But there's some additional lines that I put in here, right? Before I actually call the Matlab conv, I'm actually doing some other things. So suppose if we look at this line, nyb equals to nx1 plus nh1. So nx1 is what? nx1 is basically the starting index of the x signal, right? And then nh1 is basically the starting index of the impulse response signal, right? Because nh is like the horizontal axis of h, right? So its first element inside of the nh is actually the starting index of the h signal, right? So nyb is just going to be a summation of the starting indices of both the input signal and the impulse response. And nye is what? You can sort of see nx length of x, that's basically the last element. The last element of nx. So sometimes you use and, right? You can change it to and, right? Sometimes, and nh is sort of the last element inside of nh, which is basically the ending index of h, right? So you don't really have to use length of h to index into it. You can use just the end. That's the Matlab default. And then the horizontal axis of the y, the output signal, actually equals to nyb to nye. So it's actually starting with, so the output signal actually has the first index at nyb, which is basically the summation of the starting index of the two input signals, the input signal and the impulse response, actually. And then the ending index of the output signal is actually a summation of the ending index of these two signals, the input signal and also the impulse response. But why is that, right? Why is that? And this square bracket is actually unnecessary, right? If you actually try to optimize it, this square bracket is actually unnecessary. But why the range of the output? Why the range of the output is kind of determined by these two formulas, right? By these two formulas. So let's go back. Let's go back to look at this particular figure. So the starting index for x actually it's at 5, and then starting index for n for h is actually 1. right? So the output of the convolution is going to have a starting index that's 5 plus 1, that's 6. And then the ending index for the impulse response is 2. And then the ending index for the input signal is 7. So 7 plus 2 is 9. So the last non-zero stick is actually at location 9. But why? But why is that? Right? Why is that? So you have to look at the amount of the shift of the impulse actually. So when we actually did the shift, back, so h1 nh1 is the sig shift of nh by the amount of 5, right? So h has a starting index of 1. Shifting it by positive 5 actually makes the result of the shift h1 has a starting index of 1 plus 5, right? That's 6. So that's h1. h1 has a starting index of 6, right? And then what's going to be the ending index for h1? Because h has an ending index of 2. 2 shifted by 5, it's 7. So h1 is going to have an index that goes from like a 6 to 7. So if you don't believe me, you can just take a look at the nh1. nh1 is a 6 to 7, right? Because it's h shifted by 5. It's h shifted by 5. And then if you look at the h2, it's h shifted by 6, right? So if h starts from 1 and ends with 2, shifted by 6, it's going to start with 7 and end with 8, right? So nh2 is going to start from 7 and end with 8. And then what about h3? h3 is h shifted by 7, right? So the starting index is going to be 1 plus 7, that's 8. And then the ending index is going to be 2 plus 7, that's 9. So if you don't believe it, you can just look at nh3. That's 8 to 9. And then the output is just a superposition of those 3 shifted impulses with some weights, right? So if you add those 3 pulses, 3 shifted impulse response together, then it's going to have a range that goes from like 6 to 9. Right? So basically this equation, these two equations are basically just implementing what we just observed, right? So the beginning of the result is going to be the beginning index of the result of the convolution is going to be these two adding together, because you are essentially shifting the impulse response h by the amount that's nx1, right? So so the starting index of the result is going to be nh1 plus nx1, right? Because you are shifting the impulse by nx1. That's for the first stick in the input signal, right? And then for the last input in the signal, you're going to shift the h by how much? You're going to shift the h by nx end, right? That's the last stick inside of the input signal, right? And then what's going to be the end of the result, right? End of the convolution result, it's just a nh end, the last stick in the impulse response, and then also shifted by the last index of the input signal. So that's going to be the range of our convolution result, right? So this slide is basically just summarizing these 2 lines of codes basically. So xn, that's the input signal, has a range of xb to xe, and then the impulse response has a range that goes from hb to he. Then the output y is going to have a range that goes from nyb to nye, and nyb is going to be just the summation of the starting index for the input signal and also the starting index of the impulse response. And then the ending is going to be the ending of the output. The ending index of the output signal is just going to be this plus this, right? and that's exactly what we have implemented here, right? And we also have verified it by using this summation formula explicitly, right, inside of the command window, right? So that's how you can actually implement the convolution in Matlab in the